Hello, today we'll be talking about logarithmic functions. This is section 4.2 in your book. So when we write logarithmic functions, you write log base b of y equals x. And this b is always the base. Okay? And logarithmic functions are the inverse of exponential functions. If you want to convert a logarithmic function to an exponential function, this is what you do. So you write the base, right, that's b. Then you go to the other side and write x, b to the x equals y. Okay, so I always remember this back and forth business. You start with b, then you go to x, then you come back to y. So you go back and forth. So log base b of y equals x. It exponentially is written as b to the x equals y. Okay, so you can use this to solve logarithmic, logarithms rather. Okay. So if I want log base 10 of 100, okay, how do I write that? I write that as, so log base 10 of 100 is something, right? So that is 10 to the something equals 100. Now you think, what is that something? That something is 2, right? So 10 squared is 100. So log base 10 of 100 is equal to 2. Okay, let's do another one. Log base 10 of 1/10 is something. So that is base 10 to the something equals 1/10. Okay, and how can you convert 10 to 1/10? You write that as -1. So that something is -1. Okay. How about log base 9 of 3 is something. So we write that as log, write that as 9 to the something equals 3. Now how are 9 and 3 related? The square root of 9 is 3, and that is power 1/2. Okay, so that is 1/2. Okay. If no base is written, you assume base 10. No written base means that it's actually base 10. And we call that the common logarithm. Okay? So when you see log x, you know it means log base 10 of x. Okay, so that's what the log button on your calculator is base 10. That is the common log. Okay. If your base is e, so that's one note, and the other note is that if the base is e, remember e is this number 2.71828, then we call it natural log. Okay, so log base e of x is actually, you might have seen it as ln x. Oops. ln x. Okay, and that stands for logarithm naturale. Okay, in Latin or whatever language they invented this in. Okay, ln, and that's the ln button on the calculator. Okay, it's log base e, natural log. Okay, let's look at the properties of natural log. Okay, so the first property is natural log of 1 is what? Well, let's write this as log base e of 1 equals something, right? So that is e to the something equals 1. So what power do we raise numbers to get them to equal to 1? Well, the answer is 0, right? So natural log of 1 is 0. E to the 0 is 1, log base e of 1, so natural log of 1 is 0. Okay? Natural log of e is what? That's the second property. Well, think about this, right? We can derive this. Log base e of e equals something, right? So that's this base e to the something equals this e right here. E to the what equals e? The answer is 1. So natural log and e, right, are inverses. They kind of cancel each other out. You can think about it like that. So natural log of e is 1. Just like division and multiplication cancel each other out. You could think about it like that. Okay. Natural log of e to the x equals something. Okay, so this is log base e of e to the x. Log base e of e to the x equals something. So you want to think base e to the something equals e to the x. What is that something? X, right? E to the x gives you e to the x. So natural log of e to the x is x. So that's what we're saying. Natural log and e cancel each other out. So whatever is in the exponent is what is left over. Okay? And then the last property is e to the ln x. What is that? Alright, so e to the ln x. Let's see, do I want to write, I don't want to write this in logarithmic way, but I know that e and ln cancel each other out. So I guess you could write it like this. E to the log base e of x. And e and log base e kind of cancel each other out. If we wanted to write this logarithmically, how would we write it? We'd write it like this. Log equals something, right? Log base e of something equals log base e of x. So what goes in that something spot? The x. Okay? So again, that shows you that e and natural log cancel each other out and you're left with just x. Okay. There are some more properties that I want to go over. This is page 277 in your book. Okay. And these properties not only work for natural logs, but they work for all logs. Okay. So the log of a product is the sum of the logs. Log of a quotient. So I think these properties should actually be switched, right? You want to see, look at number 7 first. Log of a quotient is the difference of the logs. And log of a number raised to an exponent, the exponent comes out front. Okay, that's why you put the p out front. And then log of 1 over n is minus ln log. Okay, so this number 6 comes from the fact that this is like natural log of n to the negative 1, right? And then that n to the negative 1 can come out. So then you get minus natural log of n. Okay. So number 6 is really just an extension of property 8. Okay. Or you could look at it as an extension of property 7. You could say natural log of 1 minus natural log of n. Natural log of 1 is 0, so it's just minus ln n left. Okay. Let's do some examples, okay, using these properties. So first let's solve some of these. Okay, so log base 3 of 27. So that's what we did above, right? Rewrite logs as exponents. Okay, so let's rewrite these guys as exponents. So log base 3 of 27 equals something. So you want to think 3 to the something equals 27. What is that? So the answer here is 3 to the third, right? 3 to the third is 27. So the answer here is 3. Okay. Again, there's something here. 2 to the something equals 16. So 2 to the what gives me 16? 2 times 2 is 4, times 2 is 8, times 2 is 16. So that answer is 4. Okay. And then again, 16 raised to the something. Remember there's a little gap here, a little box. 16 to the something equals 4. So 16 to the what equals 4? Well, I know square root of 16 equals 4. So that is power 1/2. So log base 16 of 4 is 1/2. Log base 4 of 1/4 equals something. So that's 4 to the something equals 1/4. So that's 4 to the what power? -1. Okay. -1 is 1. 4 to the -1 is 1/4. And then 2 to the something is 1/8. Alright, so how can I get 8 in the denominator? Well, I know 2 times 2 is 4, times 2 is 8. So I know that 2 to the third is 8, right? 2 to the third is 8. But I want the 8 to be in the denominator, so I have to put a negative in front of it. So 2 to the -3 is 1/8. So that answer is -3. Okay. So notice last time we talked about the graph. I think we looked at the graph of logs, and we looked at the domain and range of logs maybe 2 sections ago. So you cannot take the log of a negative number, but your answer can be negative. Okay, and that's exactly what we have here. Okay. Log base 9 of 1/3. So that is 9 raised to the something is 1/3. So 9, how can I get 1/3? Well, I know square root of 9. Square root of 9 is 3. That's 9 to the 1/2. But if I want 3 in the denominator, I have to make that exponent negative, right? So this is my thought process. Okay, so 9 to the -1/2 is 1/3. So my answer is going to be -1/2. Okay. Let's look at the log properties. Okay. Oh, I have natural log of x to the third minus natural log of x. Alright, first thing I see, product, or power rather, exponent. Exponent can come out front. So this is actually 3 ln x minus ln x. Okay. Now you got to be a little bit careful right here. The log property says ln of m to the p. It's not this. Okay. It's not the same thing as that. Okay, so it's not the whole log being raised to the exponent, just the inside. Okay, just like here, the x is being raised to the third power. So the 3 can come out, and then remember there's like a little 1 here, right? So 3 ln x minus 1 ln x gives us 2 ln x. Okay. Oh, these problems, and I forgot to tell you, these problems are coming from your book. Let me see what page number they are on. They are on page 286. Okay, so these are on page 286. And these are just problems from the book. Number 2 we did. Okay, number 7, exercise number 7 we did. This is exercise number 9. Okay, natural log of x. So this is log of a quotient is a difference of the logs. So I'm going to subtract these. Okay, and you can see up here. Natural log of x, so natural log of m minus natural log of n. So this is natural log of x minus natural log of 4, and then plus natural log of 4. Right. Well, then these two, minus and plus, cancel each other out, and I'm left with just ln x. Okay. Natural log of e to the 5x. Well, this is one of the properties we saw earlier. What happens with natural log and e? They cancel each other out, right? Well, let me do this. Let me bring this out here first. So I have 5x natural log of e minus 2x minus natural log of 1. Okay? I know this thing equals 1, and natural log of 1 equals 0. So really I'm just left with 5x minus 2x, and this becomes 3x. Okay. So let me just box my final answers. Right? Alright, this is example 9 in your book, same section, 4.2. A sum is invested at 12% interest compounded quarterly. How soon will it double in value? Well, remember we saw this last time? Compounded quarterly, that means m is 4. Remember our formula? P1 plus r over m to the mt. At 12% interest, so that means r is 0.12. Compounded quarterly. How soon will it double in value? So I have the rate, I have m, how soon, right? So this means I need to find t. So what they don't give me is a principal, or the initial value, or the present value. But I don't need that, because it says how soon will it double in value. So if I start off with p, that means if it doubles in value, then I'm going to be left with 2p, isn't it? So if I start off with 100 as p, I want it to double in value, I want to get 200. Okay. So let me go ahead and plug in what I know. 1 plus 0.12 over 4 raised to the 4t. Okay, and then t is what I'm solving for. Now right off the bat, you can see I have a variable, the same variable on both sides, p and p. I can divide out, right? And then that's gone, and I'm left with 2 equals 1. And then let me just do everything in one step here. 0.12 divided by 4 is 0.03, right? 12 divided by 4 is 3, and then you move the decimal 2 spaces to the left. So that's 1.03 raised to the 4t. Okay? So that is the equation I want to solve for t. Now, how can I get the t by itself? This is where natural log comes in. Okay? If I take the natural log of both sides, and I always write my ln like this, not to confuse it with 1 times n. Okay, it's just a habit I developed early on. Something I recommend you guys do too. ln of 2 is equal to ln of 1.03, and it's this. Okay, now I can use my properties of logs, because I know now when I take the ln, this part will come out front. Okay, so then I have ln2 equals 4t times ln 1.03. Okay, now ln 1.03 is a number. That's like a number, like 5 or 10 or whatever that number happens to be. Okay, and I'm multiplying here. It's 4t times ln 1.03. So I want to divide both sides by ln 1.03. I want to get the t by itself, remember. And then I can actually go ahead and divide by that 4, right? 4 ln 1.03. And then I'm left with t equals ln2 divided by 4 ln 1.03. Do you see that? So the 4's cancel out here. Let me change my color. The 4's cancel out, and the ln 1.03 divided by ln 1.03 is 1. So I'm left with t on the left side, and then all this on the right side. Now, let me show you how to plug this into the calculator. Okay? So you're going to do ln2. Now you can plug this in all at once, or you can do it in steps. ln2 divided by, and let me just put a parenthesis just to be safe, 4 ln 1.03. And you close the parentheses, right? So it's ln2 divided by 4 ln 1.03, and we get 5.86. That is what t is. So t is roughly 5.86 years. Okay? So that's how long it'll take for my money to double if it's invested at 12% interest compounded quarterly, no matter how much money I have in the bank. So if I have $1,000 or $2, it's going to take about 5.86, 5.9, roughly 6 years to double. Okay, let's look at another example, another real-life application of exponents and logs. So all living things absorb small amounts of radioactive carbon-14 from the atmosphere. Okay, and this is also from your book. This is page 282. Okay. So when a living thing dies, the carbon-14 stops being absorbed and decays exponentially into ordinary carbon. Therefore, the proportion of carbon-14 still present in a fossil or other ancient remain can be used to estimate how old it is. Okay, so that's what they call carbon dating. The proportion of the original carbon-14 that will be present after t years is given by this function here. E to the negative 0.00012t. Okay, so you can see by this little graph here, the amount of carbon-14 to be reduced by half is what, approximately 5,000 and some years. Okay, so it takes a long time, right? So if we know the amount of carbon left, or the proportion of carbon left, we can figure out how old that object is, right? So here's an interesting example. That's ancient history. Now I love ancient history, so this is a bonus for me. The Dead Sea Scrolls discovered in a cave near the Dead Sea in what was then Jordan, and this is example 12 in your book. So the Dead Sea Scrolls are among the earliest documents of Western civilization. Estimate the age of the Dead Sea Scrolls if the animal skins on which some were written contain 78% of the original carbon-14, right? So the animal skins are alive. We can use carbon dating on that. All right, 78% is remaining, right? So look at this formula up here. The left-hand side is the proportion of carbon-14 remaining. So how much carbon-14 is remaining? 78%. What's that as a decimal? 0.78. So 0.78 is the left side, and then the right side is this function here, e to the negative 0.00012t. Okay? Now we want to get the t by itself, right? So we have to get rid of that e. So what we want to do is take the ln of both sides, ln, and then I know I have ln of 0.78, right? And then this whole thing moves out to the front, 0.00012t, ln e, right? I know this ln e is 1, so really I'm left with 0.00012t, and then I can divide both sides by negative 0.00012, oops, negative 0.00012, and then I'm left with t equals this thing right here on the left. So let's go ahead and plug that into our calculator. So let me do this so I can see the left side. Where's my, so clear this. We can do all this at once, right? So ln 0.78, close off that parentheses, and then what does that give me? Now if you want to do this all at once, I always like to do this because I'm never sure if the calculator, let me do second insert, second delete is insert, and put another parentheses here, and then do second right arrow and it'll go back to the end. I'm never sure if it'll do ln 0.78 or if it's only going to divide the 0.78, but just to be safe I do this, 0.00012. Again, you can do this in pieces, okay? And we get 2070.5. So t is roughly, so let's change that to approximately 2070 and a half years. Okay? Alright, so that is all of section 4.2. For your active learning or your practice problems, you can work on 22 and 32, or you can work on some odd problems nearby just to get some examples or practice, and then check your answers in the back of the book. And then also work on the homework. And if you have any questions, feel free to get in touch with me. Okay. Thank you for watching.